Okay, so the size of the atomic force microscope is so small that it can fit in the distance or in the gap between the objective and the slide platform, okay, or stage of the compound light microscope. Okay, but the cost is very high. It is beyond 1 crore. And the reason is that the probe is a very, very fine probe which can go very close to the sample surface. It can actually feel the surface. It moves along the surface, okay, in the XY direction. And it also goes up and down, okay, to trace the contours of the sample surface or actually see the topology of the surface. And it takes the point by point image in the sense that the movement of the probe is observed by the laser beam, okay, and a detector. The detector will see how the probe is moving along on the surface, and that movement will be actually the information from that will be used to construct the image of the surface, okay, and therefore we get something like a three-dimensional image of the surface. And then since this particular mechanism is not dependent upon the flow of electrons, okay, we do not really require a conducting sample, and even an insulating sample or a biological specimen can be observed without any problem. And in fact, even if that biological specimen is in water or any aqueous medium, even then we can observe that specimen by using the atomic force microscope. And that is to say that we can actually observe the real time object or the object in real time. Okay, so for example, whatever reactions we may be carrying out, if you are putting some, for example, if you are trying to see the phototaxi or chemotaxi, that phenomenon also probably you can probably see. Okay. Then coming to the three different modes of operation. One is called as the contact mode. So this I have already explained to you that at a distance of 0.4 nanometer from the tip of the probe to the sample surface, okay, there is an attractive force, and that attractive force is used for imaging. In the non-contact mode, as I told you, because in the contact mode, there is a probability that the probe might break if it encounters or if it collides against the sample, some feature on that sample surface. And therefore, people go for what is called as the non-contact mode, where the repulsive force between the sample probe and the probe and the sample surface is used for imaging. And because of that, the tip will not actually collide with the sample features. Okay. And then but there may be a chance, sometimes there is still a chance that the probe might collide with the features on the surface, and therefore it might break. And therefore there is a third mode, which is called as a tapping mode. And this kind of a mode is a very, very interesting mode where the tip goes close to the sample surface, okay, but not too close. Okay, it is not going so close to the sample surface where the attractive or repulsive forces are dominant. Okay, in fact, the distance is a little greater, and at that particular greater distance, this particular probe is actually oscillating. So can you see my movement? I'm showing here on the video, my own video. Okay, the probe is actually oscillating like this, or it is vibrating. Okay, so it goes to the sample surface and it is not still, it is actually vibrating. And then it is tracing the sample surface like this. Okay, so it is scanning the surface, but the probe is actually oscillating, right? And why it is oscillating, the reason is very interesting. I'll try to show it here in the form of an animation, a small video clip. There are in fact two clips which I have taken at my own house. Okay, and with that example, I'll try to tell you about the oscillating probe. Okay. Can you see my screen?
Yes, sir.
Yes.
काय दिसतंय तुम्हाला सांगा बरं का. On the window screen here, okay, there is an insect. Can you see that insect?
Yes, sir.
Yes, sir.
And what is it doing? You want to see that again? Okay, I have another image. I'll show that. Can you see the antenna? Can you see the antenna moving?
Yes, sir.
Yes,
Yes.
sir.
Okay, very good. So what is it doing? Why is it moving the antenna?
Sensing the environment.
It find the direction. I
Yes,
think.
it is sensing the environment for any possible threat. Okay.
Yes, yes.
Sorry. Where is the presentation? Okay. Can you see that? Okay. So I was trying to notice what it is doing. I was very curious about that, and I was trying to shake it away by waving my hand or something, or just shouting hard, hard, hard. But that insect was not moving. Okay. And then what I did was I brought my finger close to that insect and I started moving my finger like this. Okay, very fast, as if it was his own antenna. Okay, with the same kind of frequency, I was moving my finger. And interestingly, what happened is when the frequency of my finger movement probably matched with the frequency of the antenna, the insect moved a little back and suddenly it flew away. Okay, so what happened? What happened? I was moving my finger, it was vibrating like this, and the antenna of the beetle was also vibrating. And when the frequency of the vibrations matched, at that particular point of time, the insect could sense something, it could sense danger probably. And because of that, that insect actually flew away. Okay. So what I'm trying to tell you is we have already seen such kind of thing in our spectroscopies also. Okay, where we have seen the phenomenon of resonance. Okay, when the particular radiation interacts with matter, okay, in that interaction, if the wavelength of that interaction is a certain wavelength, and that matches with, as we have seen in the vibration mode, infrared spectroscopy, okay, when the molecules are vibrating, and if the frequency of the vibration and frequency of the wavelength are matching, then that molecule is going to absorb the radiation. Okay, so this is something like the same phenomenon where there are vibrations, and these vibrations are sensed by the detection system or the antenna. And that is why the insect knew that there was some danger around and it went away. Is it right? So in the atomic force microscope, we are actually making use of a similar principle where the probe is vibrating. Okay, it goes close to the sample, and the sample molecules are also vibrating. Sample itself is vibrating because anything in the world, it is not stagnant, it is not stable, but there are vibrations everywhere, isn't it? So these vibrations of the probe are matching with the vibrations of the sample atoms. Okay, and as long as the vibrations are matching, as long as there is radiation, as long as there is some resonance that is sensed by a detector. Okay, and while the probe is scanning, is vibrating, oscillating, and it scans the sample in the different directions, the XY direction. Okay, if there is some feature on the surface, if there are some molecules on the surface, then there will be an alteration in that vibration. Okay, and because of that, the instrument will automatically tell the probe to go up. Okay, up, up, up. And then if there is a depression on the sample surface, then that vibration will not be sensed by the tip, and therefore the instrument will push the tip back very close to the sample. So in this particular way, the instrument is trying to monitor the vibration, and the vibration should be constant. Okay, the signal of the vibration should remain constant, and for that purpose, the instrument will keep the probe close to the sample at a particular distance. Okay, and as the probe moves along the sample surface, whatever features are there on the surface, the ups and downs, they will be monitored by the detection system. Is it right? So this kind of a mode is called as the tapping mode. Okay. So we have contact mode where attractive forces are used, non-contact mode where the repulsive forces are used. And the third interesting mode is called as a tapping mode, where the oscillations in the sample and the oscillations in the probe, they are used to make that image. Okay, so just look at some of the features, which are some of the figures that I have taken from the net. And then very interestingly, you will find that there are two things which are happening. One is you get the image of the surface. Can you see the image of the surface?
Yes, sir.
Okay, this is a three-dimensional image. That is one thing. The other important thing is as the probe is moving up and down, okay, and it is moving along the surface. Okay, so its movement exactly, okay, it is tracing the movement, it is actually tracing the surface, okay, sample surface, okay, and as it is tracing, as it is moving up and down, every movement is detected by the detector. And in fact, for example, suppose the probe is moving from this point to this point, which is the elevation, okay, the distance which is traveled by the probe from this point to this point is measured and it is recorded. Okay, the distance which the probe goes from the top level to the bottom level in the depression, okay, from the top of the mountain and to the base of the valley, that distance is also calculated. That distance can be monitored and it is recorded by the instrument. Okay, so what I'm trying to say is that every movement of the probe is detected by the detector and it is recorded. The distance which is traveled by the probe at every point, okay, that distance up and down or along the surface, all the distances are recorded, and therefore the dimensions of every feature on the surface can be recorded. That information is made available. Okay, so I'll just zoom this image for you to understand this. Can you see this lower diagram here? In the lower diagram, they have given the dimensions. Okay, the surface which is scanned, the dimensions of that, and the dimension of each and every feature on the surface, the height, the length, the breadth, everything is available, everything is recorded. Could you see that? Can you see this
Yes, sir.
lower image?
Yes, sir.
Okay.
Yes, yes.
So does it make any create any interest in your mind? Okay, so we are not only taking the image of the surface, but we are also trying to get information of each and every surface feature. Okay, each and every surface feature, we can calculate the dimension, the size. Okay, so for example, if it is a bacterial cell, then we will be in a position to find out the length of the bacterial cell, the breadth of the bacterial cell. If there are flagella on the bacterial surface, then the dimensions of the flagella can also be determined. We can find out the size of the flagella, the length of the flagella, the breadth of the flagella, or the diameter of the flagella. All that information can be made available. Is it right?
Yes, sir.
Yeah. Now this is again an example where the tapping mode was used. Tapping mode in atomic force microscopy was used to scan the surface of a contact lens. Contact lens, मालूम है ना? That is put in the eyes. Okay. Nowadays people have a craze for that. A lot of craze is there. Okay. So this contact lens surface is actually imaged using the atomic force microscope. And then here somewhere you find that there is some problem. There is a defect here. Can you see that defect? There's a big hole here, pit is there, or a depression is there. And then this is the place where bacterial growth will probably take place. Okay, so if the surface is not uniform, or if there are some depressions or some deformities in the surface, then that is the place where bacterial, you can say, contamination can take place, and that will lead to bacterial growth, and that might subsequently result in bacterial infection of the eyes. Okay, eye infections can take place in that particular way. Okay, so leave that thing apart. I think I have something else to show you. I'll go to the next slide. force to the distance curve. Now this is again an important feature where how much you can actually touch the surface with the probe. Okay, a particular surface can be touched with a probe like this. Okay, and then what I can do is just imagine this thing, that I can press the surface. Okay, I can press the surface and then I can release the probe. Okay, and then I can monitor how much time it takes for that particular surface to regain the normal shape. Okay, I am pressing the surface like this. Okay, and then I am removing the probe. So how much time is taken for by the surface to regain the original form? That particular kind of analysis will tell me about the stiffness of that particular surface. Stiffness, or you can say elasticity of that surface. Do you understand what I'm saying? So what the instrument
Yes.
will do here is it will try to measure how much force was applied. Okay, and then how much time also it takes for the surface to regain the original structure. And based upon that, the characteristic feature of the surface in terms of the stiffness of the surface or elasticity of the surface, or you can say the strength, mechanical strength of that surface, all these different parameters can be analyzed. Okay, so remember that this is a microscope with a difference. It is not just a simple microscope. It is allowing you to find out certain characteristics of the surface. Okay, that may be the strength of the surface, the mechanical strength, or the stiffness or elasticity. Okay, and that is not all. There are some other things also that we can see. Let me go to the other slides if I have that information. Okay, this is the image taken for a kidney cell. Okay, kidney cell from a canine. Okay. So what is shown here is not only the intracellular components of the cell. Okay, they are clearly seen here, but you can also see all the measurements here. Every feature in that cell is observable, it is visible, and not only that, but the dimensions of each of the components in the cell, they are also analyzed. Can you see that here? Okay, all the dimensions are also available. Right. So for example, just look at this, the height of this particular feature, okay, is 185 nanometer. Right. This is again a very interesting image where they have a kidney cell. Okay, and in the kidney cell, certain proteins are there. Okay, protein clusters are there in the membrane, associated with the membrane. Okay, and these protein cells, these protein clusters, they are trying to analyze what is happening to the protein in a particular situation. For example, ATP is added. You know what is ATP? Okay, so when ATP is added, just look at this is the control where no ATP is added, and then 30 seconds after ATP addition, can you see that the size of the cluster has become smaller? Okay, it has become still smaller, and then at the end of 10 minutes, you see that the protein cluster is virtually gone. It is absent now. Okay, so the proteins have moved away, and that was the response to the addition of ATP. In other words, the atomic force microscope can give you real-time images of any biochemical reaction that is taking place in a cell. Okay. So is that interesting? And if it is not very interesting, then I will tell you another interesting fact, and that is not only can you observe the thing, observe a surface using the atomic force microscope, but you can also carry out certain kinds of manipulations. Like in the case of the IBM logo, I have told you that 35 atoms of xenon were actually collected, they were placed on the surface, they were arranged in the form of the letters. Okay, and the same thing was again imaged by the scanning tunneling microscope, of course, that was, but that can also be done with the atomic force microscope. That is to say, the attractive property of the probe, okay, can be used to collect the particular molecules or atoms on the surface. Okay, and the repulsive force of the probe can be used to push the atoms on the surface. Okay, so you can collect the atoms and you can push the atoms. You can pattern the atoms on a particular surface, atoms or molecules. Okay, it could be nanoparticles also. So all that manipulation can be done. And not only the manipulation is done, but the same probe can also be used to carry out the imaging part. Okay, so manipulation plus observation both can be done using the atomic force microscope.
Sir, sir, once the atoms are arranged,
Hmm.
sir, won't they relocate from the surface of the
Uh,
thing? I mean, the surface where
they
the
will not relocate because the surface is a special surface. Okay, so just imagine that it is a sticky surface, for example. Okay, it is like a sticky surface. So, for example, if it was a nickel surface, we have seen that in the case of xenon atoms. So, nickel surface will have that particular property of attracting those atoms. So, whatever atoms are placed on the surface, they will remain there for a long time. Okay. And then you see here that this picture is again very interesting. Instead of using just one probe here, there are two probes which are working together. Okay, so for example, one probe is doing the manipulation job and the other probe is doing the imaging part. Okay, two probes together. Right? Is it interesting?
yes, sir.
Yes.
Yes or no? Okay. Then there is more interest now when I tell you that in this particular image, you can see that there are four probes working together. There are four probes together. So one probe is doing something, other probe is doing something else. Third probe is again doing a different job. And the fourth one is taking the image of everything. Is it right? Very interesting. And then now I'll add one important bit of information here, that what the four probes are doing actually is probably one of the four is a probe is a magnetic probe. Okay, in the sense that this particular probe is able to, determine the magnetic properties of your sample. Try to understand this. One probe is detecting the magnetic properties of the sample. One probe is detecting some other property, some other physical property, maybe the conductivity of the sample, whether it is conducting or non-conducting. Okay, so different probes are doing different kinds of actions, different kinds of analysis. And therefore, this microscope is not just a microscope. It is able to manipulate your atoms and molecules. Not only that, but this microscope is also giving you a qualitative analysis of your sample. Okay, it is trying to determine the physical properties of your sample. Is it right? So it is like a miracle device. Okay, it can do so many things together. Okay, just try to imagine how different things are done. And then one more application of an atomic force microscope is nanolithography, where you can actually go close to the sample surface. Your probe is a hard probe. It is like a diamond, for example, diamond probe. Okay, it is very hard. And then this probe can actually cut some features on the surface. Okay, it can do something like engraving. You know what is engraving? Okay, that is called
Yes, sir.
nanolithography. So it can actually, what I can say, carve out something. Okay, carve out some features from that particular sample. Okay. And then the piezoelectric kind of a device is used. I think I have not told you about this particular thing. That is again very important. When I told you that there is a cantilever, and on the cantilever there is a probe which is mounted. Okay, like something like this. The probe is mounted on the cantilever, and because of the movement of the cantilever, the probe is moving on the surface. Okay, this way it is scanning the surface, right? So the movement of this cantilever is because of a special type of a material which is called as a piezoelectric crystal. Okay, so the special property of the piezoelectric crystal is that if you apply a small voltage, okay, small voltage difference if you create, okay, then this piezoelectric crystal will increase in the size or it will decrease in the size. Okay, so length of the crystal will change when you apply a voltage, and that voltage is a very, very small voltage. And therefore, the change in the length of the crystal is very, very small. It is a few nanometers. It is that small. Okay. And it is because of that movement of the piezoelectric crystal that the probe which is placed on that crystal will actually move, or it will scan the surface. Do you understand what I'm saying? So movement of the probe on the cantilever, okay, or rather the movement of the cantilever is because of the piezoelectric properties of a material which is called piezoelectric crystal. Is it right? I think I had that image somewhere in my presentation. Shall I go a bit backwards? I'll just try to show it to you. Yeah, here it is. I'll increase that size. Okay, can you see this one? This is a quartz. This is a quartz crystal actually, and it has piezoelectric properties. And the advantage here is that if there is a electrical field or a voltage difference, then the material will vibrate, or it will increase or decrease in the size. And that increase or decrease in the size will be used for movement of the probe on the surface. Okay, because the movement is a very fine movement. Okay, it is not like the movement of my finger. Okay, it is a very fine movement. Okay, now this is something very, very interesting for biology students like you. Okay, what is written here? Can you see the image? Can you see this D, letter D? Yes.
Yes, sir. DNA.
DNA, very good. Okay. You know what is this material which is used here for making that shape?
So maybe it's engraved.
Maybe.
It is engraved.
I couldn't hear you. Can you be a bit loud?
Sir, maybe it is engraved.
Engraved. Okay. Okay, then I'll tell you the answer. You will be very, very surprised to know that this material itself is DNA. Is it interesting?
Yes.
The material used for making this letter itself is DNA, and this DNA is made like that. Okay, it is made in that particular shape by using an atomic force microscope. Okay, so atomic force microscope is actually used to cut the DNA at certain places. Okay, and then make that particular shape and put it on a surface. Okay, not only that, but it is also taking the image of that surface. The photograph is obtained by atomic force microscope itself. Right? And that actually makes me to say something, some interesting statement. And that is, have you heard about restriction enzymes? What are restriction enzymes?
Yes.
Yes,
Yes,
sir.
sir.
Yes.
What are they?
Yes. Molecular scissors.
Molecular scissors
Molecular.
that cut the DNA, isn't it? These scissors cut the DNA,
Yes.
right? So now, interestingly, what I want to tell you is we don't require any restriction enzymes. We can cut the DNA by using an atomic force microscope. Okay, DNA has been cut into pieces using atomic force microscope. The DNA has been aligned on the surface again by using an atomic force microscope. And the image also can be obtained by using an atomic force microscope. Right? And therefore, I'm saying that this is a very, very wonderful type of a device. It can do so many things at the same time. And yeah, then that is not all. Again, you can work with this atomic force microscope in air. You can work in water, or you can work in vacuum. You can work with bacteria in liquid medium. Okay, so anything you can do in any type of a sample, you can carry out the imaging studies. And then I will tell you the last slide of my presentation tells you that these are the different types of atomic probe microscopies, okay, or scanning probe microscopies. We have already seen the atomic force microscope. There is something called as a magnetic force microscope. There is a scanning tunneling microscope. There is a chemical force microscope, conductive AFM, electrostatic force microscope, electrochemical STM, Kelvin probe force microscopy, magnetic resonance force microscopy, and so on and so forth. There are so many different types of microscopes. And the speciality of all these microscopes is that each one is able to carry out a certain kind of analysis of the sample. Okay. And probably I have asked you one question. What was the question? Okay, before that question, I want to tell you again one important thing, that the size of the probe is very, very fine, very small probe. It is a very, very thin probe. It is thinner than your hair. Okay, it is thinner than the hair. And therefore, the problem is if I just blow air, okay, this way, then what will happen? The probe is going to drift in air. Okay, drift in space. Can you understand what I'm saying? The probe
Yes,
is
sir.
so fine that if you just blow air on the probe is going to move. And then just imagine that if you are using the atomic force microscope to scan a particular sample, okay, and then if there are a lot of vibrations on the floor, suppose somebody is running in the corridor, like in our institute, many students have the habit of running in the corridors. So if you are running in the corridor, then what will happen? That vibration will create an effect on the movement of the probe, because the probe is so small and it is so close to the sample surface that even a tiny vibration anywhere in the surrounding, that will affect your observation, imaging, isn't it? And therefore, these microscopes are normally mounted on a special kind of a surface, on a special kind of a table, which is called as a vibration-free table or a vibration-free surface. Okay, so what I have shown here on the slide are some images of the table, and on this table, the atomic force microscope is actually mounted on a normal microscope, that is compound light microscope is there, and on that on the sample stage, the atomic force microscope is mounted there, and it is going to scan the sample surface, and all that is happening in an environment which is totally vibration free. Okay, and it is this microscope actually is floating on that table. So even if there are vibrations, these vibrations will be absorbed by the surface, and therefore the scanning process will not be affected. Is it right? Okay. So this part I'm going to deal with later. I think I've already told you so many things about the applications that I don't need to read this particular slide again. Okay. So my question was one thing, why this particular topic is included in spectroscopy. That was my question. Okay, and the answer to this question is is now probably you will be able to understand it, that there are so many different types of probe microscopies, and these different kinds of probe microscopies are going to give you some information about your sample. Okay, some physical or chemical properties of your sample. Okay, and therefore this is not just a technique to visualize the sample surface, but it is also a technique to characterize the sample, and therefore it comes into the category of a spectroscopic method. Do you understand what I'm saying?
Yes, sir.
This
Yes,
is not
sir.
only a microscope for observation, this is also a device for manipulation, and it is also an instrument, analytical instrument for carrying out different types of spectroscopies. Is it right? Okay. And then I think I wanted to tell you something.
Yes.
One thing I have left out. Okay, this is very interesting. Okay, the atomic force microscope is placed under the objective of a normal microscope. It is placed on the sample stage of a microscope. Okay, and then you can act using the eyepiece. Okay, so you can observe through the eyepiece of the normal microscope where the probe is there. Okay, so for example, if you have a slide with a bacterial smear on it, okay, you can prepare a bacterial smear, or maybe you take a culture drop, okay, drop of a bacterial culture, you put it on that particular slide, okay, and then the tip of the probe will go very close to the sample, okay, and this can be observed through the eyepiece of the microscope. Okay, using the normal compound light microscope, you can see the tip which is placed close to the sample surface. Okay, and then you can by using certain knobs which are there. Okay, or there is a machine with the software, necessary software. So using that kind of a software, you can allow the probe to go very, very close to the sample, to the exact place where you want it to go. And then you can start the scanning process so that the probe will now start scanning the surface on its own. Okay, so what I wanted to tell you here actually is it is a microscope within a microscope. What is it? It is a microscope within a microscope. That is to say, with the normal compound light microscope, you are able to observe the atomic force microscope, the movement of the probe. You can actually see the probe moving on the sample. Is it right? So that was the point which I forgot to tell you. Have you all understood?
Yes, sir.
Yes, sir.
And then we come to the end of the presentation. I have the last slide, which is interesting statement for you all. Okay, and that is the summary. The summary says normally we have the we say that seeing is believing, isn't it? Unless you see something with your own eyes, you cannot believe it. Okay, seeing is believing. So with the advent of these new types of microscopes, now I am prone to, or rather I am, you can say, inspired to say this, that feeling is believing. Okay, so these are special types of microscopes which don't see the object, but they actually feel the object. Okay, they feel the object. Okay, so that is the end of this particular lecture. I think we had 4 long sessions and hope it was interesting to all of you. If you have any questions,
Yes, sir.
then you can ask me. In the meanwhile, I'll have some coffee. Okay, you can also have your own cup of coffee. Any questions?
No, sir.
No questions. Anything you want to comment on this type of microscope? If it is an interesting field, then you should have something to say, something to discuss. Let us look at the applications. Imaging inorganic surfaces.